The outline is I'm first gonna just like sort of plagiarize my advisor for maybe 10 minutes. And then I'm gonna put my entire PhD thesis into a single slide. But first I have to explain the title of the thesis, what it is and what it's not. And then I'm gonna claim to make a prediction that some of the results that I proved in my thesis can actually just be proved from large cardinals instead of assuming this ultrapower axiom. And then I'm going to confirm the prediction. I guess I confirmed the prediction before I made it. Not actually. So there are going to be a bunch of, can you hear the drilling? Okay, so there are a bunch of different applications. First one is about indecomposable ultrafilters and a question of silver. And then there's something about, it's a question of Caicedo about something called cardinal preserving elementary embeddings, which are like sort of close to the Kunen inconsistency. Then there's going to be the actual Kunen inconsistency and its relationship with ultrafilter combinatorics. And then there's just some inner model. So I don't know if I'll go through all of it. I was just, this is 2 hours, right? Or Victoria, is it actually 2 hours?
Well, it's
1.5.
1.5, okay. Okay, so this is wooden stock now. I'm going to try not to subconsciously imitate his mannerisms. So the covering theorem for L can be formulated as a dichotomy. Either L has covering or zero sharp exists, so L is really small and every uncountable cardinal looks like an inaccessible cardinal to L. Which it means that covering can't hold because like aleph omega is inaccessible in L, so you can't cover the alephans. Okay, and then Wooden proved a HOD dichotomy, the HOD dichotomy theorem, and it's in the context instead of large cardinals. So if you have an extendable cardinal delta, then either HOD has exactly the same covering property as L above delta, or else every regular cardinal is measurable in HOD and above delta. So there's a slight difference here, right? This says regular instead of every cardinal. And there's a reason, right? Like aleph omega is always singular in HOD, right? Because the aleph ends are ordinal definable. And similarly, delta plus omega is going to be singular in HOD. So you can't get every cardinal to be inaccessible in HOD. It's just impossible. Okay, so HOD has some largeness properties that L doesn't have. I mean, that just necessarily does. Okay, so yeah, this covering property is called the Jensen covering property past a cardinal. Okay, so for L has the Jensen covering property past aleph 2, meaning, for every set of size less than aleph 2, you can cover it. Set of the same, well, yeah. Sorry, okay. And Wooden's HOD conjecture is the assertion that you can prove in ZFC that HOD has the Jensen covering property past the least extendable cardinal. Okay, or it's equivalent to that. It's usually formulated in terms of omega strongly measurable cardinals, which are the negation of some property. But in the context of an extendable cardinal, many of these things coincide. So the question is, I mean, okay, so the thing is, everyone believes that you can't prove in ZFC that the Jensen covering property holds for L, right? Or else I wouldn't be talking about extendable cardinals. But so why would you conjecture that you could prove the Jensen covering property for HOD? That's sort of interesting difference between these two dichotomies. I mean, they are clearly pretty different. Okay, so large cardinals already imply that L doesn't have the Jensen covering property. On the other hand, every large cardinal that's consistent with ZFC that we know of is consistent with V is equal to HOD. And the thing about V is equal to HOD is it has no consequences except for the axiom of choice. Basically, I mean, the result is, I think, McAllen, that, you know, V equals HOD can't prove any new sigma 2 sentences over ZFC, because you can always force without changing a level of V to code. I think that's right. Maybe it's pi 2. Okay, so the inner model problem. So this is the real reason you might make the HOD conjecture. So the inner model problem for a large cardinal is the problem of defining a canonical inner model in which the large cardinal axiom holds, so a generalization of L. So the thing is, you want this generalization to answer all questions in set theory, like V is equal to L, but you want it to be consistent with large cardinals, so you have to balance those two things. Okay, so it's sort of amazing that the inner model problem can be solved for large cardinals. You can't build canonical models of other axioms. I mean, usually, really, there are no other canonical, there aren't models like this for any other axioms. But so that's sort of a special thing about large cardinals. Okay, so some names. I think that currently the best outright model is due to Sargsyan and Trang. I don't really remember what the large cardinal in it was, but it's something above a wooden limit of woodens, which is was the current. I mean, it was the previous world record set by Niemann, and then under hypotheses, Wooden and Niemann Steel built models which have cardinals kappa that are kappa plus n supercompact. Okay, so that's a really large cardinal in a canonical model. Okay, but the inner model problem for kappa plus omega supercompact is still open. So you can, and it's still open for anything past like Sargsyan and Trang's model, so it's still open for a super strong. But that's a different problem. There are really two problems. Anyway, okay, so the inner model problem for supercompacts. So just notation. So for every large cardinal, such that the inner model problem has been solved for it, every stronger large cardinal axiom refutes the axiom, V is L of A, L sub A, the generalization of L to A. So what does all stronger large cardinal axioms mean? It's not really true. If you just add an inaccessible, it's not going to refute. This is sort of looks like it's saying that two inaccessible cardinals will refute V equals L. So I mean significantly stronger, like a measurable past one or whatever, the next large cardinal. Okay, but Wooden's work suggests that this pattern breaks down in a supercompact. So if you build the backgrounded model for a supercompact, so that means its large cardinals are coming from actual large cardinals of V, then this model should actually have all large cardinals. So it's called ultimate L. And the reason it should have all large cardinals is this phenomenon, which has applications in large cardinal theory outside of supercompactness, which is that you can sort of encode lots of stuff into a supercompactness measure. So For example, you can encode lots of different forcings into supercompact Percury forcing. A supercompactness measure is going to be Ruden-Kiesler above all the ultrafilters on smaller cardinals. So that it's sort of, as these measures get bigger, they become universal for smaller objects, especially for large cardinal-like objects. So that there's another tension here, right? So you can encode all the large cardinals into supercompactness measures, and those measures are supposed to be in ultimate L. So all the large cardinals are supposed to go to ultimate L. But if the supercompactness measures are actually coding too much information, then you're not going to be able to build a canonical model for them, right? So if too much is encoded into these measures, then there won't be an ultimate L at all. Okay. So the ultimate L conjecture makes all this precise, or it's really a test question which approximates this kind of speculation that there's a canonical ultimate in our model. But I'm not going to say what it is. But anyway, if the ultimate L conjecture is provable, then the HOD conjecture is true. So there's some subtlety here. I had to think about Loeb's theorem. The reason, though, is that the ultimate L conjecture gives you this large inner model, which has all large cardinals, and it has all these covering properties. And this inner model satisfies V equals HOD because it satisfies the axiom V is ultimate L, which implies V is equal to HOD. And it turns out that if you have a large inner model that satisfies V is HOD, then the HOD conjecture has to hold if there's an extendable. So that's due to me. So the ultimate L conjecture used to have this ad hoc thing in it that said that ultimate L is contained in HOD. And that was how you got the HOD conjecture, but you don't actually need it. Okay. So what is the ultrapower axiom not? So we're going, I finished Wooden's talk. Okay, so it's not, well, some more Wooden. It's not the ultrafilter axiom. That's all I wanted to say about what it's not. This is not the ultrapower axiom. So there was something else called the ultrafilter axiom that Wooden defined. You don't have to read it, but I guess it got to me subconsciously. And I think that maybe when I first named the ultrapower axiom, it was the ultrafilter axiom, and then I realized, and it became the ultrapower axiom, which is anyway more over the top. Okay, so notation for ultrapowers. If U is an ultrafilter and use the ultrapower, it's sort of annoying sometimes because you want to talk about the ultrapower of M by an ultrafilter U, and then it's MU of M, and it's not clear when the M is a function and when the M is a model, but it works usually. Okay, so if U is countably complete, MU is well-founded, that's an equivalence, and it's, I mean, the most important property of countably complete ultrafilters. So under DC, whatever. Okay, and because we're set theorists, we identify it with its transitive collapse, which everyone else thinks is weird. Okay, so an inner model obtained this way is an ultrapower. I guess some of this, I never know if this is too self-explanatory. So an internal ultrapower of a model is an inner model of that model that the model thinks is an ultrapower. Okay, and the same conventions for ultrapower embeddings. So an internal ultrapower embedding of a model is an embedding of the model thinks is an internal ultrapower. And these things are sort of first order in the predicates. And I really should work with the set sized objects, but it becomes tedious. Okay, so what's the ultrapower axiom? What the ultrapower axiom is. Okay, so the weak ultrapower axiom says if you take any two ultrapowers of V, they have a common internal ultrapower. Okay, so sort of natural thing to state. And then the ultrapower axiom is the weak ultrapower axiom plus whenever you have an ultrapower of V, there's a unique ultrapower embedding into it. Okay, so this is a different way of stating the ultrapower axiom, so I don't have to talk about commutative diagrams. It's a little ad hoc. Okay, so this is sort of, some category is filtered. And actually the category of ultrapowers under the ultrapower axiom is a lattice. So it has least upper bounds, and the weirder one is greatest lower bounds. Okay, but I guess maybe, I hope I said, yeah, ultrapowers are always inner models. So I'm ruling out ultrapowers by countably incomplete ultrafilters that way when I talk about ultrapowers. And the reason is that the ultrapower axiom is false for them. It's false for ultrapowers by ultrafilters on omega. Okay, so then there's another way of formulating the ultrapower axiom that's more natural. So whenever you have two ultrapower embeddings of V, you can find further internal ultrapower embeddings to a common ultrapower M, N, and the diagram commutes. Okay, so the ultrapower axiom, well, it has a lot of consequences that look like the properties of the known canonical inner models. Oh, I think I went to the wrong slide. Okay, so why should the ultrapower axiom be consistent with large cardinals? It should hold in ultimate L because it's true in all canonical inner models that we know of. So if there is an ultimate L, the ultrapower axiom should hold in it. So, but there is a precise, statement of the axiom V is ultimate L, and you can ask, does that imply the ultrapower axiom? And that's open. So the axiom V is ultimate L involves all these HODs of determinacy models. And for example, HOD of L of R, assuming AD L of R, satisfies the ultrapower axiom. And so do all the HODs of small determinacy models. So the HOD of the minimal model of ADR is a model of the ultrapower axiom. And the reason is people have analyzed the models as canonical inner models. And that's how you prove they satisfy the ultrapower axiom. But maybe there's some abstract way to prove that the HOD of a determinacy model always satisfies the ultrapower axiom. That would make me really happy. Anyway, so if there are no measurable cardinals, then UA is vacuously true because it's talking about these ultrapowers. If there are non-trivial ultrapowers, then there's a measurable cardinal. So UA is totally useless if you don't have large cardinals. Or really, you can prove implications from UA, like if there isn't. But and that's how I state everything anyway. But if you have large cardinals, UA becomes extremely powerful. Even at the first measurable cardinal, you get a complete classification of all the embeddings with critical point kappa that, short extender embeddings. And it's just exactly like the Kunen classification of embeddings of L of U, right? Every embedding involving just the first measurable cardinal is just an iteration of the unique normal measure on the first measurable cardinal. Okay, but with very large cardinals, UA becomes, ultra powerful. So it's so UA answers lots of questions about the category of ultrapowers, which I think are pretty interesting. Like it's a lattice, but if you have a strongly compact cardinal, you can actually encode lots of set theoretic structures into the category or super compact cardinal. So this is the same embedding into supercompactness measures phenomenon we were talking about before. And then using UA, you can solve classical set theoretic questions by embedding them into questions about measures. Okay, so here's some examples. So this is my thesis in a page. Okay, so suppose kappa is a strongly compact cardinal. Then the GCH is true beyond kappa. V is a generic extension of HOD for a fairly small forcing. The forcing is size less than or equal to kappa double plus in HOD. It's not known whether the forcing, whether you can bound it any better than that. But you can prove the Jensen covering property for HOD beyond kappa. So, you know, if you're a generic extension for a forcing of size less than or equal to kappa plus plus, it's not clear if you have the Jensen covering property beyond kappa. It's just you have a very strong covering property beyond kappa triple plus or something. Okay, so you can prove diamonds in combinatorial principles, although there are open questions there. So, but there's a definable diamond sequence, definable from parameters, and the parameters are actually they're close to V kappa. The parameter is a subset of V kappa. But okay, diamond holds definably over H lambda double plus. So H lambda double plus is definably well ordered, an order type lambda double plus. Okay, so the Mitchell order is linear on normal fine ultrafilters. So all supercompactness measures are linearly ordered by the Mitchell order. This is actually for the Wooden and Neiman steel models, this is the proof of the linearity of the Mitchell order. Is just UA implies it. The other proof breaks down. And then there's the large cardinal consequences. So if kappa is strongly compact, it's either supercompact or a limit of supercompacts. So supercompactness and strong compactness are equivalent under UA. Okay, so now the prediction. So if the ultimate L conjecture is true, then there's an inner model of V is ultimate L, and it should satisfy UA, and it has all large cardinals above the least extendable cardinal, beyond the least. So one of its properties necessarily under the ultimate L conjecture. So the reason I have all these conditional verbs is it's not clear whether V is ultimate L implies UA. So this model should satisfy UA, but I'm more certain of UA than V is ultimate L. Okay, so it sees all delta complete ultrafilters in the sense that if you have a delta complete ultrafilter U, then the intersection of U with this inner model is in the inner model. And it actually even sees their associated elementary embeddings, although the correspondence could be off, provably. It could be that you take the ultrapower by the intersection with the model, and it's not the right embedding, even though the inner model can define the embedding. So that's a common thing in core model theory, or all over set theory. Okay, so as a consequence of this, you sort of turn it around. It's not just that the inner model sees the large cardinal structure of V, it's that the inner model controls the large cardinal structure of V, because the ultrapower axiom has strong effects on large cardinals. And so those effects have to sort of affect what's true in V. And so you should predict, if you believe the ultimate L conjecture, that consequences of UA are provable from large cardinals. And okay, I said that I was predicting something that I had already confirmed, but actually I guess that I thought this would be true, and I wrote it in my thesis, and I actually confirmed it after I predicted it. So that's an actual confirmation. So it's supposed to be evidence that V is ultimate L is true. So here are the results. And also there's a chance that I just see UA in everything. So it's like, whatever, the number 23. Okay, so I just like this picture. So for ultrafilter combinatories, have you guys seen this? There's a whole thing called an ultrafilter in like plumbing or something. This guy can't spell, so pressure gauge and tubular ultrafilter. But I don't know, he patented something with all these typos. Okay, but yeah, so different kind of combinatorics. Okay, so what's an indecomposable ultrafilter? So it's from the 70s. People wanted to understand the interaction, I guess, between countably incomplete ultrafilters and countably complete ultrafilters. So indecomposability is like the closest a countably incomplete ultrafilter can get to being countably complete, or it's an approximation. There are, I guess, some stronger things. So U is a uniform ultrafilter if all the sets in U have the same cardinality. This is just some non-standard thing. U cover is a family of sets whose union belongs to U. Okay, so it's a U cover of the underlying set of U modulo null set. Okay, so then indecomposability is you can express it. It looks like compactness, even though it sort of shouldn't. Okay, so if kappa and delta are cardinals, then U is kappa delta indecomposable. If every U cover of cardinality less than delta has a U subcover of cardinality less than kappa. Okay, so it looks like whatever these. Okay, so uniform ultrafilter is indecomposable if it's omega 1 lambda indecomposable. So that means whenever you have like a partition of the underlying set of U into fewer than lambda many pieces, you can find a subpartition into countably many pieces that already has union of full measure. Okay. Maybe I should be a little slower on this. So yeah, so notice that an ultrafilter is lambda complete if and only if it's omega lambda indecomposable or 2 lambda indecomposable. Those are the same. Omega lambda indecomposable says that whenever you partition the underlying set, you can find a finite subpartition that's in the ultrafilter, whose union is in the ultrafilter. Okay, but if you have a finite partition whose union is in the ultrafilter, you can get just one of them in the ultrafilter because, you know, an ultrafilter is sort of defined to have exactly that property. Okay, so if you're omega lambda indecomposable, you can always take any partition and find a single element, any partition of size less than lambda, and find a single element that belongs to the ultrafilter. Right, so that's the definition of lambda completeness, or one of the many equivalent definitions of lambda completeness. Okay, so Silver asked this question. If you have an inaccessible cardinal and it carries the closest possible thing to an indecomposable ultrafilter, must the cardinal be measurable? Okay, and I don't think he thought that this had a positive answer. He just, he said, like, we don't even know if this could be answered. This is a question that obviously looks like it's going to be independent. If you think about indecomposable ultrafilters for a while, it doesn't feel like you can do this. So first of all, the reason for inaccessible here is that if you have countably many measurable cardinals, well, one reason, and you take their limit, then that always has an indecomposable ultrafilter on it. So it's a singular cardinal, but it carries an indecomposable ultrafilter. So indecomposability does not imply lambda completeness. And the way you get it is you just take omega many increasingly complete ultrafilters and you take their limit, you put them together. Okay. And then exactly the same argument basically shows that every measurable cardinal carries an indecomposable ultrafilter that's not countably complete. So that means you can't give a direct answer to Silver's question, right? Because it's not like you're going to take your indecomposable ultrafilter and then just prove that it's lambda complete, because that's not true. So you might hope you could extract from the ultrafilter a lambda complete ultrafilter or something like that, which is what we're going to do. But oh yeah, the other thing I was supposed to say is another example is if you take a measurable cardinal, just one, and you prick force to make it have cofinality omega, you take the normal measure from the ground model, any extension of that to an ultrafilter in the generic extension is indecomposable. Okay, so Silver's question, they answered it in the 70s or 80s. It's independent. So on one side, there's the canonical intermodels. What's true in them? Well, these really hard core model theoretic arguments give that the consistency strength of an indecomposable ultrafilter is exactly one measurable. So that's due to Donder, that there are these, preliminary results going back to Silver. Okay, so the proof, I guess Donder's proof uses strong versions of square, which is weird because, if you see below, it's weird because square and strongly compacts are supposed to be the opposite of each other. But I'd guess, so I didn't check because it's really hard for me to read core model theory, but the proof, I guess, would probably generalize to all the inner models and show that that on inaccessible cardinals that aren't measurable, so if you're not measurable, you satisfy some strong enough square property to refute the existence of an indecomposable ultrafilter. That's my guess, but it's no one ever wrote that down. So the question is, how large are the cardinals you can get that are consistent with a positive answer to Silver's question, right? Because Silver's question is vacuously true if there are no indecomposable ultrafilters. Okay, so by forcing Sheard, who's a student of Solovey, built, this is his thesis, a model where there's an inaccessible cardinal. It's not even weakly compact, but it does carry an indecomposable ultrafilter. Okay, so it's independent. Definitely in L of U, there's this measurable. The measurable cardinal is the only cardinal that carries an indecomposable ultrafilter. Okay, so Silver's question is true there, and there's a measurable and indecomposable. Okay, so UA resolves a version of Silver's question. So UA is, as far as I know, it's only useful for solving questions about countably complete ultrafilters. It has minor implications for countably incomplete ones. So if so the generalized version of Silver's conjecture is this: if you have an inaccessible cardinal that carries, so lambda, that carries a kappa lambda indecomposable ultrafilter, then lambda should be measurable. So for any kappa strictly less than lambda. The reason, if you want to have a non-trivial version of this, for countably complete ultrafilters, you better not just say indecomposable, because any countably complete indecomposable ultrafilter is automatically lambda complete. Okay, so you need to generalize it to say something non-trivial for countably complete ultrafilters, but UA proves exactly what Silver wanted. And this is a little bit more general. It's not just that you analyze the inaccessible cardinals, you also get an analysis of the singular cardinals that carry indecomposable ultrafilters. Okay, so if you're a singular cardinal and you carry an indecomposable ultrafilter for a small enough cardinal, then you actually have to be a limit of measurables, and you get a complete analysis of the ultrafilters, but it only works for countably incomplete. Okay, but it turns out, that large cardinals, so strongly compacts, just one strongly compact, resolves Silver's question asymptotically. So beyond the strongly compact, you can resolve Silver's question, even though you couldn't in CFC. So the indecomposable ultrafilter theorem I proved is that if you have two cardinals and they're separated by a strongly compact cardinal, and there's a kappa lambda indecomposable ultrafilter on the bigger cardinal, then lambda is the soup of fewer than kappa measurables. Okay, so if lambda is inaccessible, then it is measurable, right? Because it has cofinality greater than kappa. In fact, you don't even need an inaccessible, you just need regular. Okay, so let's see. So the case of Silver's conjecture is just the case when kappa is omega-1 and lambda is regular, right? That's saying if lambda is inaccessible and it carries an omega-1 lambda indecomposable ultrafilter, which is just an indecomposable ultrafilter, then it's the supremum of countably many measurables, but since it's regular, it's just the supremum of one measurable, which is measurable. Okay, so how do you prove? I didn't want to call it the indecomposable ultrafilter theorem, but then I got weird grammatical constructions. Anyway, so how do you prove the theorem? So there are two results that go into the theorem. One of them, this one is due to me. So if delta is strong and compact and you have an ultrafilter in V delta, then every mu kappa complete mu ultrafilter belongs to mu. So this is saying that ultrapowers by small ultrafilters absorb large cardinals above strongly compact. Okay, and the strongly compact cardinal here is necessary. I have counterexamples. If you only have a lambda strongly compact cardinal, then you get counterexamples near lambda. So let's see. Why is it the approximation property for ultrapowers? Another theorem I proved is that this property, if you have an inner model M and it has the kappa cover property, which is a weak version of the Jensen, say the delta cover property. The second kappa here should be a delta. I'm sorry.
Okay. Yeah. Okay, that's what I was going to ask.
Yeah. Sorry about that.
I got confused.
Mm-hmm. So if you have an inner model with a delta cover property, then it has the delta approximation property if and only if it absorbs ultrafilters in this way, if delta is strongly compact. And that's sort of the key to these results. So this is the same as the approximation property for ultrapowers by small measures. Okay, so Wooden and Usuba proved a weaker version of this. So it assumed U was countably complete, kappa delta was super compact, and the mu ultrafilter on the inner model was supposed to be truly delta complete. Okay, which means if you take the intersection of fewer than delta sets, many sets in it, that's big. So that actually the last part is the most important difference, but it turns out you can prove true kappa completeness, or delta completeness from mu delta completeness when you have covering property. Okay, so sorry about the deltas and the kappas. Okay, the other important fact, which is why I changed kappa to delta and messed everything up, is that you can factor indecomposable ultrafilters. So you have an indecomposable ultrafilter W, and you can break it apart into an ultrafilter on omega, followed by a very complete ultrafilter on the ultrapower. Okay, so if you have, here's the generalization. If you have a kappa lambda indecomposable ultrafilter, then you can find an ultrafilter that's on a cardinal smaller than lambda, and an mu lambda complete ultrafilter on the ultrapower, and the the iteration gives you back the original ultrapower embedding. Okay, I don't know if everyone thinks of it that way. There's a combinatorial way to think about it in terms of something called a finest partition. But I don't get that. Okay, so I wanted to say how you combine these two things. So the idea is sort of obvious. You have this ultrapower mu, and you have an mu ultrafilter that's giving you this iteration. And you need the ultrapower to absorb the second iterand, and then it'll have a very complete ultrafilter in it, and so you'll get some measurable cardinals. Okay, so you combine Silver's factorization theorem with this approximation property, and that tells you that this external iterated ultrapower was actually an internal iterated ultrapower, which means that the second part of the ultrapower was witnessing a measurable cardinal. Okay, so that's the basic idea. That's exactly the same as the proof under UA of the generalized Silver's theorem. You apply Silver's factorization theorem, and then you use UA to show that the ultrafilter has to be internal to the second ultrapower. Okay, so now, okay, why should you care about, I mean, it's not the 70s. Why should you care about indecomposable ultrafilters? Okay, so there's an application, and also I had this great slide. Okay, so it says, examples of typical ultrafilter applications of elements in the food and beverage industry will become evident in the following pages. I have no idea what an ultrafilter is anymore. Okay, so the application is to cardinal preserving embeddings. So J from V to M is cardinal preserving if M is an inner model that correctly computes cardinals. Okay, so it can compute successor cardinals, it's the same thing. So this looks like, you know, it's like a consequence of being an embedding from V to V, but you just took that consequence, and now you can no longer refute the embedding. But okay, so these embeddings are really weird. They shouldn't exist. It's not a real large cardinal, whatever that means. Okay, so Caicedo asked, can there be a non-trivial cardinal preserving embedding? And even though the embedding shouldn't exist, it's really, I found it really hard to refute it. I think maybe cardinal preserving embedding is somehow consistent because like just always escapes you. But anyway, so what's the relationship with the Kunen inconsistency? So first, the critical sequence is just of any embedding, you just start with the critical point and you iterate J on it. And the point is you're getting kappa 0, and then J of kappa 0 is kappa 1, and then J of that is kappa 2. And you want to go all the way up to kappa omega, which will be the first fixed point of J. As long as J is continuous at kappa omega. So this is just like you have an elementary embedding, but you're applying like the most elementary fact in set theory that you can get a fixed point of a continuous function on the ordinals. Okay, so the embedding will be continuous at kappa omega if the embedding preserves omega. So if it correctly computes the cofinality of lambda, then it'll be continuous at any cof omega point. Okay, so the theorem of Kunen, the Kunen inconsistency theorem, is that there's a stronger version. If you take J from V to M, you look at this kappa omega of J, then call that lambda, V lambda plus 1 is not contained in M. So it's a structural, I don't know, why not? It's a weird theorem. It's a disturbing theorem, I think. Like, if the same thing happened for, you can have a kappa plus n supercompact for any n, but you can't have a kappa plus omega supercompact cardinal. That wouldn't be good. And this is saying you can have an n huge cardinal for any n, maybe, but you can't have an omega huge cardinal. And that's not good. That's weird. Okay, so there's more than just an analogy between cardinal preserving embeddings and Reinhardt embeddings. Under UA, they're the same thing. So what does that mean? I'm really talking about rank to rank embeddings. So if you have a rank of V, you assume UA, you have an elementary embedding from V delta to M, where M has the same height as V delta, and M correctly computes cardinals, then in fact, this is a rank to rank embedding. So if you look at its, its kappa omega, you have all of V lambda contained in the target model. Okay, so, you can actually bound the height of M, and it's the best possible bound, because if you have the axiom I2, then for arbitrarily large cardinals below lambda plus kappa, you can get elementary embeddings like this, V lambda contained in the target model and are cardinal correct. Okay, so short of refuting a large cardinal axiom or refuting UA from a large cardinal axiom, whichever way you look at it, this is the best possible result. And it's sort of nice that UA just comes that close to refuting this very strong large cardinal, but doesn't do it. And it's, it's a very important part of the proof. So it's sort of another suggestion that UA is consistent with these really large cardinals. Okay, so as a corollary, there are no cardinal preserving embeddings under UA, because if you had a J from V to M, and it was fully cardinal preserving, then it would have arbitrarily, I didn't write this in the right way. Oh, well, I guess it's fine. Then delta is less than you can restrict the embedding down to another rank initial segment, and you're going to contradict this this bound on the height of the rank initial segments that can have cardinal preserving embeddings, right? So the idea is, if you have a J from V to M that's cardinal preserving, well, you go up to its kappa omega, and then you go up past its kappa omega to kappa omega plus kappa omega, and that embedding violates, if you take delta to be lambda plus lambda upper plus lambda, the lambda successor cardinal of lambda, then the embedding restricted to V delta violates this theorem above, because delta is too big. Okay, so what about strongly compact cardinals? Well, they prove exactly the same thing if you have enough of them. So if you have a proper class of strongly compact cardinals, then there just are no cardinal preserving embeddings. The nice thing about this theorem is if you look at the HOD conjecture, if the HOD conjecture is true, then a Reinhardt cardinal should be inconsistent with a proper class of supercompact cardinals or strongly compact cardinals. So this is, it's funny that the hypothesis is exactly the sort of thing you would use to refute Reinhardt cardinals in ZF if you knew the HOD conjecture was true. So, okay, so this is a new version of the Kunen inconsistency, I guess, right? This is refuting a different large cardinal axiom. Anyway, the theorem, a little bit more technical theorem, is that if you have a J from V to M, and you have any limit of strongly compact cardinals, then it fails to correctly compute the kappa plus second successor of this fixed point. Okay, You know, that's best possible. Because actually, if you have a j from b to m and you look at a fixed point of it, all cardinals between lambda and lambda plus kappa plus 1 are correctly computed. So the first place it could be wrong is lambda plus kappa plus 2. And if you have enough strongly compact cardinals, you can prove it is wrong. Okay, so why does it correctly compute cardinals between lambda and lambda plus kappa plus 1? So you have this fixed point, lambda. It's getting mapped to itself. We'll look at lambda plus. It's also getting mapped to lambda plus, and lambda double plus is getting mapped to lambda double plus. So that means the cardinals are being correctly computed on the m side, right? Because what this thinks is kappa is lambda plus maps over to what this thinks is j of lambda plus, and therefore j of lambda plus is fixed. So so that means that lambda plus is equal to j of lambda plus, but j of lambda is lambda. Okay, so for every alpha less than kappa, that shows you that this is correctly computing cardinals. And then when you get up to lambda plus kappa, well, that's correct because it's the supremum of all of them. And then lambda plus kappa plus 1 takes a slightly different argument. But I'm not going to go into it. Okay, so it has to be right about all the cardinals up to lambda plus kappa plus 1. And if lambda was a limit of strongly compact cardinals, it has to be wrong about lambda plus kappa plus 2. Okay, so it's a weird structural property of elementary embeddings, and it's particularly weird that you need large cardinals to prove it. I don't think that there are many other theorems like that. Okay, so what does this have to do with the previous theorem? It's supposed to be an application of ultrafilters to the food and beverage industry. An indecomposable ultrafilter theorem actually implies a cardinal incorrectness theorem. Okay, sorry about the indefinite articles. So let me sketch the proof. I think that otherwise I won't take enough time, but this might, I worry that I may be confusing people, but I can't see your faces, so whatever. Okay, so we're trying to prove this this theorem that lambda plus kappa plus 2 is not correctly computed. So it's a proof by contradiction, and I'm just going to cite the indecomposable ultrafilter theorem, which we vaguely sketched. Okay, so assume towards a contradiction that lambda plus kappa plus 2 of m is a cardinal. So then, by what I was saying before, it has to actually be lambda plus kappa plus 2. Right, because you're cardinal correct up to lambda plus kappa plus 1. So if you're correct at lambda plus kappa plus 2 of m, that means that it correctly computed the successor. Okay, and that means that lambda plus kappa has to shoot up past lambda plus kappa plus 2. Because j of lambda plus kappa, I mean, this is the first cardinal that's going to be moved above lambda. Right, so you have all these cardinals, lambda plus alpha are fixed until you get to lambda plus kappa. Because kappa is the critical point, kappa goes up, so lambda plus kappa has to go up to lambda plus j of kappa, and that has to be bigger than lambda plus kappa plus 2, because j of kappa is bigger than kappa plus 2. Okay, so this is the problem is that you shot lambda plus kappa up higher than you can possibly shoot it. Okay, so, and how do you sort of use that? Most of this proof is sort of taking well-known extender theory and taking out the extender so that it's more accessible, but it makes me look clever. All these arguments are probably due to other people. Okay, so you take y equal to what happens when you move every less than lambda size subset of lambda plus kappa. Okay, it'll be clear why we're doing that in a second. Okay, so we'll want to compute the cardinality of this set. It's not that hard. So you have the cardinality of y is lambda times lambda plus kappa to the less than lambda. And that's just because you're taking the union over lambda plus kappa to the less than lambda, many less than lambda size sets. Why is J of A of size less than lambda when A is of size less than lambda? Well, it's because you're fixing lambda. Okay, so that's where we're using the lambda as a fixed point. Okay, and that's lambda plus kappa to the less than lambda. And then another important thing here is that that's equal to lambda plus kappa plus 1. And this is applying your strongly compact cardinals to get SCH. Okay. So now you take an ordinal that's not in Y. So you can get an ordinal that's not in Y because Y is smaller than lambda plus kappa plus 2, and lambda plus kappa is getting shot up above lambda plus kappa plus 2. So there has to be an ordinal that's not in Y. And now you derive an ultrafilter from that ordinal. And the point is that this ultrafilter is going to be indecomposable, and it's going to be uniform on lambda plus kappa. And that is going to contradict the, well, not the, it's going to contradict an indecomposable ultrafilter theorem. And that means, so that's what's going to happen. The reason it contradicts any indecomposable ultrafilter theorem is that lambda plus, the indecomposable ultrafilter theorem says that if lambda plus kappa carries this indecomposable ultrafilter, then lambda plus kappa has to be a limit of measurable cardinals, but lambda plus kappa is not a limit of measurable cardinals, right? It only has all these, accessible cardinals below it. Okay. So that's the idea here. So why is this thing? So we have to check two things about the ultrafilter. First, that so for it to be, well, it's going to be, for it to be indecomposable. Well, it's not going to be fully indecomposable because it's going to be countably complete. But that's why I wanted to state the generalized Silver's question. Okay, so it's going to be countably incomplete. Countably complete. Okay, so it's going to be indecomposable. It's going to be rho lambda plus kappa indecomposable for some rho below lambda. Okay, that's what we need. And for that to be true, we want lambda plus, it needs to be a uniform ultrafilter on lambda plus kappa. For us to apply the theorem, we need a uniform ultrafilter that is rho lambda plus kappa indecomposable for some rho less than lambda. Those cardinals are separated by a strongly compact cardinal because lambda is a limit of strongly compact cardinals. And any indecomposable ultrafilter theorem told us that if you had two cardinals separated by a strongly compact cardinal and you had a rho lambda indecomposable ultrafilter on lambda that was on lambda plus kappa that's uniform, then lambda plus kappa has to be a limit of fewer than rho many measurable cardinals. Okay, so that's not true. It's not measurable because it's singular, and it's not a limit of measurables. Okay. So we have to show U is uniform, and we have to show that it's rho lambda plus kappa indecomposable, or really what I'm going to show is lambda plus kappa indecomposable. So why is U uniform? That's the whole point of why. If U isn't uniform, there's some set A in U that's smaller than lambda plus kappa. So Xi is in J of A, but the definition of Y is that it's J of A for all the small sets, right? So Y is the union of J of A for all small sets A, and we took a Xi that wasn't in Y, so that means Xi definitely can't be in J of A for a small set. So that means this derived ultrafilter U is uniform. Okay, can't have a small set in it. Okay, and then we can prove that U is also lambda plus kappa indecomposable. the reason for this is, if you look at the ultrapower embedding by U, it's fixing every cardinal between lambda and lambda plus kappa, right? And if an ultrafilter is decomposable, that means it's discontinuous at a cardinal. That's what decomposability really means in terms of elementary embedding. So because it fixes all these cardinals, it has to be indecomposable and with respect to them. Okay, and I wrote down a proof of that, but I feel like I'm a little incomprehensible, so probably should not speak it. Okay, there's the proof. I don't really approve of Beamer proofs, but I've been told that you have to give a proof. Okay, so now this is just the contradiction I was saying. So you go from a lambda plus kappa indecomposable to a rho lambda plus kappa indecomposable using food and beverage trade secret. But you can move this cardinal down because lambda is fixed basically, and because you have SCH. But that's a little one more argument. And then, there's a strongly compact cardinal between this rho and lambda plus kappa by the assumption that lambda is the limit of strongly compacts. And you have an indecomposable, you have a rho lambda plus kappa indecomposable ultrafilter. So lambda plus kappa is measurable, or a limit of measurables, and that's a contradiction. Okay, so you apply the indecomposable ultrafilter theorem and you prove the non-existence of these cardinal preserving embeddings. So cardinal preserving embeddings give you weird ultrafilters that can exist if you have enough strongly compact cardinals. By the way, I guess I didn't say, why does a cardinal incorrectness theorem imply the theorem above it? The point is, if you have a proper class of strongly compact cardinals, and you have this J from B to M, you can get a limit of strongly compact cardinals that's fixed by J. Okay, because you just you do the same trick with the critical sequence. You take the least strongly compact cardinal and you move it by J. You take the least strongly compact cardinal above it and you move it by J. You go up, you take the limit, and that's fixed by J. Okay, so I do have time for these. So this is about the result that HOD is a generic extension of V. So an inner model is a ground if V is a set forcing extension of it. Okay, so there's a partial order in M generic filter G that exists in V, and V is equal to M of G. M satisfies CFC. That's really important for the theory of grounds. I mean, V can have grounds that satisfy CF, and there's no theory developed for those, or there's, Usuba's developed some, but it doesn't work as well. Definitely not. Okay, so under UA, if kappa is strongly compact, then HOD is a ground. I already stated that theorem. Okay, so now what can you get in just ZFC plus large cardinals? I mean, the reason to look at stuff like this is that you want to prove the HOD conjecture. The HOD conjecture is like the ultimate, well, let's not say ultimate again, the holy grail of all these inner model-like theorems for V under large cardinals is to prove the HOD conjecture. So, okay, what can you get? I didn't prove the HOD conjecture. Okay, so I proved the HCD conjecture. It's not a good acronym. Okay, so a set is kappa completely definable if it's definable from a kappa complete ultrafilter on a normal. And that means definable in V from a kappa complete ultrafilter on an ordinal, which of course is not first order, but the same reflection theorem that shows that HOD is first order shows that this is first order. Or you could just say it's ordinal definable from a kappa complete ultrafilter on an ordinal, which is the same thing as definable from a kappa complete ultrafilter. Okay. So HCD is the hereditarily kappa completely definable sets. So union of the transitive closure. Never mind. if the transitive closure of a set is everything in it is kappa completely definable, then it's HCD. Okay. So what do these models look like? We have V on one side, and V turns out to be equal to the omega completely definable sets. Just you can code lots of stuff into countably incomplete ultrafilters. They're bad. Okay, but HCD of omega 1 is the countably complete ultrafilters, and that's not necessarily equal to V. The reason is that HCD omega 1 is invariant under forcing smaller than the least measurable cardinal, or let's say forcing smaller than the least inaccessible cardinal. It's just like a Levi-Solovay theorem. All the ultrafilters in the generic extension, well, let's say homogeneous forcing. Okay, so homogeneous definable forcing below the least inaccessible cardinal is going to preserve HCD. So like if you add a Cohen rail, because it preserves ordinal definability, and it preserves all the countably complete ultrafilters. Okay, so or at least it makes HCD smaller, maybe if you add if you do homogeneous forcing. So that means that you can't prove V is HCD of a cardinal bigger than omega. And then HCD infinity. So infinity is, the Burali-Forti cardinal. So it's bigger than all the cardinals. HCD infinity is just HOD because an infinity complete ultrafilter is principal, especially one on an ordinal. Okay, so if cap is strongly compact, then HCD is a ground. Okay, so that's weird because these models are shrinking as kappa gets bigger. So why is kappa strongly compact telling you that HCD is a ground? Well, the important thing actually is that it's not clear that HCD is a model of ZFC for any of these HCDs. Well, it's just not obvious, right? Because the parameters are kappa complete ultrafilters, and there's no obvious well order of the kappa complete ultrafilters on ordinals. But at the level of a strongly compact cardinal, you can prove that HCD of kappa is a model of ZFC. And that allows you to prove its ground. Okay, and the interesting thing about that is that there are no other grounds that are provably from large cardinal exists and are possibly non-trivial. Okay, so this is, that arise in nature outside of set theoretic geology. So in set theoretic geology, you define like the mantle, but that's defined in terms of the notion of a ground. This is just defined in terms of the notion of a kappa complete ultrafilter, and it somehow gave you this giant model that V is a forcing extension of, and V could be a non-trivial forcing extension of it. So first natural example of a ground, non-trivially. Okay, so
how do you show that it's a ground, Gabe?
I vaguely remember you show you define a relativized HCD of kappa, and then you show that HCD kappa sub A is actually equal to V whenever A codes up a well ordering of V kappa. And then you prove Bopenka's theorem for HCD, which says that HCD of A is a set forcing extension of HCD. Okay, so the HCD of A proof, the proof that HCD kappa sub A is equal to V is exactly the same proof as, well, there's a proof under UA that if kappa is strongly compact, then V is equal to HOD sub A, where A is any well order. And the proof only uses that every countably complete ultrafilter is ordinal definable under UA. So if you add in all the ultrafilters, then you get a ground just by the same proof. Okay.
Gabe, could I just ask, when you consider HCD of kappa, just in general, can you restrict the collection of ultrafilters that you use? Is it set sized? Like, can you find a set sized collection of ultrafilters that are to be used when forming HCD of kappa?
I would guess that you can't prove that HCD kappa is equal to HCD of a set sized collection of ultrafilters.
Okay.
Because you're using these ultrafilters to encode more and more about V. So if you forced to add, undefinable stuff, I think you could mess that up.
Okay.
You force above the ultrafilters. Okay, so that's all I have to say about HOD. I mean, I think these kinds of things, not this, but the other things look like close or something that is getting closer to the HOD conjecture. Of course, there's also another great inner model theorem that's already been proved due to Usuba, who proved if kappa is extendable or delta is extendable, then the mantle is a ground for delta CC forcing. So it's proving an almost inner model theorem. The canonical inner models should satisfy the ground axiom. So, V is ultimate L implies the ground axiom. So this is proving a close consequence of V is ultimate L. So that's another one of these theorems. It's better than these. Okay.
Wait, sorry, can I just ask one more question about this result? So Usuba's result that you mentioned, I'm pretty sure part of what it says is if you have delta extendable, then there's less than delta many grounds. Is that true here, where under UA, if kappa is the least strongly compact, then there's less than kappa many grounds?
I don't think that Usuba proved that. He proved that there's delta many grounds. Maybe that's less than or equal to delta many grounds.
Yes, sorry, right. Yeah.
Okay. No, I didn't prove that. I mean, that would be an improvement on Usuba's result, right? But I can't do that. So I think that probably for Usuba's result, extendable is best possible. But I probably would have said that about hyperhuge. Okay. So one last thing in the last 4 minutes. So I'm going to talk about the choiceless cardinals for just a second. And what do they have to do with UA? Or how do I hallucinate about UA with the choiceless cardinals? Okay, so what's the Kettenin order? First, we're looking at homomorphisms of Boolean algebras. And the definition is that a homomorphism is Lipschitz if whenever you take a set in P of delta, it moves the minimum of the set up. If you play around with that, that's equivalent to exactly the Lipschitz property, but okay, this is, I didn't want to have an overfull V box, so I gave a shorter and simpler definition, but maybe less natural. Okay, so the Kettenin order at delta is the order that's induced by these countably complete Lipschitz functions. Like it's countably complete Lipschitz reducibility. So it's an algebraic version of the Lipschitz order from generalized descriptive set theory on ultrafilters. So if you have U and W, you put U below W in the Kettenin order. If there's a countably complete Lipschitz function H from P of delta to P of delta that reduces U to W. So if you want to know whether a set's in U, you apply H and ask whether H of A is in W and A is in U if and only if H of A is in W. So this reducibility is called the Kettenin order. Kettenin defined a special case. I defined the general case. But it's like, it's like the generalization of the Lipschitz order, of the Mitchell order on normal measures to all ultrafilters. And this is the right one. Okay, so in ZF plus DC, and that's going to be a little important below, you can prove that the Kettenin order is well-founded. And if you formulate UA correctly, you can prove that UA holds if and only if the Kettenin order is linear at every ordinal. So you have to be careful about how you formulate UA in this context, because you don't have Wash's theorem if you don't assume CFC. Okay, but the Kettenin order is well-founded. That's going to be important to us. Okay, so the last slide. Okay, so you can look at choiceless cardinals. If you drop AC, you can look at cardinals that are stronger than the ones that Kunen refuted. Okay, one reason to do that is it's just so weird that the large cardinals end at the Kunen inconsistency. Another reason to do that, to look at the choiceless large cardinals, is that choiceless large cardinals refute the HOD conjecture, the proof theoretic HOD conjecture. So you sort of want to understand, is that refuting this whole picture? Are they all the choiceless cardinals consistent, and everything I'm doing is just sort of crazy, or is it the other way around? The HOD conjecture refutes the choiceless large cardinals, and so the HOD conjecture is true, and that means that the choiceless large cardinal hierarchy actually is constrained in some way. Okay, so a revised Reinhardt cardinal is the kappa omega of J of a Reinhardt embedding J from V to V. It's a better definition of a Reinhardt cardinal. Sort of interesting question. I'm sorry, I'm going over time, but the critical point of a Reinhardt cardinal can never be first order definable over V. Can a revised Reinhardt cardinal be definable over V? And then the more interesting question is, can you define revised Reinhardt cardinals first order? I think it's sort of plausible that you can. Okay, but I'm working in second order set theory. Okay, so the ultrafilters on delta of rank C, I'm going to call that U delta C. Okay, so if UA holds, then that set has size less than or equal to 1, because the Kettenin order is a linear order, right? It's going to have size 1 until you get up past the Kettenin rank of delta. Okay, so that's an equivalence. Okay, so suppose lambda is a revised Reinhardt cardinal, and assume lambda DC. So this means that lambda is the least revised Reinhardt cardinal, right? Because lambda DC is true. So I guess that answers the question, can a revised Reinhardt cardinal be definable? Well, yeah, because it could be the first point where choice fails. Okay, so this is the first failure of choice. Okay, so what do you prove? You can show that, the levels of the Kettenin order are all smaller than the least revised Reinhardt cardinal. So UA almost holds, right? It's the Kettenin order is almost linear in this context. So that's weird. It's best possible, because you could force to make it bigger. Actually, the Kettenin order is provably not linear in this context, because I'm not gonna go there. Okay, you can use the Kettenin order also to show that lambda plus is strongly compact. This should say every lambda plus complete filter on an ordinal extends to a lambda plus complete ultrafilter, but I guess I stated a false result in order to not have an overfull V box. Okay, and the last thing is you can use this result exactly, the almost linearity of the Kettenin order, to analyze the ordinal definability of ultrafilters and actually show that HOD is in some ways large under choiceless large cardinals. So HOD absorbs all ultrafilters. Okay, and that's really strange, because these large cardinal axioms are supposed to be like HOD sharp, right? They're the ones that refute the Jensen covering property for HOD. So they should be the sharp of HOD, and yet they're showing that in some ways HOD is a large model. And in the ZFC context, it's weird. If you have these properties, then lambda plus is a strongly compact cardinal, and HOD is absorbing all ultrafilters. And remember from way back that if you had the covering property would imply the approximation property and refute everything. But anyway, that argument won't work. And as promised, thanks. Okay, that's it. Can I stop sharing my screen? Yeah.
Sure.
Any questions?
Yeah, are there any further questions for Gabe?
Thanks, Giannis. Okay, so I think there aren't any questions unless there's something
Looks
in the
like
chat.
it.
Okay. Well,
I have a question.
Who's talking to me?
This is Monroe.
Okay, hey.
Hi.
You.
So the results about the non-existence of a cardinal correct embedding.
Mm-hmm.
Are you assuming that the embedding is amenable to V in the theorem?
Yeah, so I'm working in NBG, so the embedding is amenable to V, and yeah, so otherwise, I'm not sure what theory you're working in, but if you have a J from L to L, it's cardinal preserving.
Right. Okay.
Yeah, there's another interesting question in Andres's paper. Can you have a cardinal preserving embedding from M into V? And those are even weirder. I just never thought about those.
So, Gabe,
Yeah.
you said you wrote one of these proofs down. Are they available or?
Yeah, they're in this archive paper called Some Combinatorial Properties of Ultimate L and V, which is named after.
Like the Kunen Jensen paper. Yeah. Very good. Okay. That's it. No more questions? Okay.
Okay.
All right. Thanks a lot.
Yeah, thanks for inviting me.
Thank you.
Gabe, it was a fantastic talk. I really, really enjoyed it.
Thanks. I used images that I did not have the copyright to.
We'll keep quiet.
Ooh.
I think that they won't sue me, the ultrafilter people in the beverage industry.
Do you think it's okay if I post it publicly, the recording?
I don't know. I was wondering, do you think that the ultrafilter theorists, in whatever plumbing, also are aware of us? Like, do they think it's funny?
Maybe they will be.
Yeah, soon, once I'll see them in court. Okay. Bye.
All right. Bye-bye.